Swayam Prabha. Digital India. Educated India.
In my previous session, I had discussed regarding the first process in the digital image processing, that was statistical examination of the remote sensing data. Having performed this, the next step in digital image processing is rectification and restoration. Image rectification and restoration refers to those operations which are preliminary to the main analysis. It produces a corrected image that is as close as possible, both radiometrically and geometrically, to the radiant energy characteristics of the original scene. In order to correct the image data, internal and external errors must be determined. The internal errors are due to the sensor itself. These errors are systematic in nature and constant, and thus can be known from pre-launch or in-flight calibration measurements. External errors, which are unsystematic in nature, are due to perturbations of the platform and modulation of scene characteristics. These unsystematic errors can be determined by relating known ground points to their corresponding points in the image. Typical pre-processing operations include radiometric and geometric corrections. First of all, let us look at some of the radiometric corrections which have to be done. First is atmospheric correction. While discussing the initial statistics, it was found that remote sensing data in the visible bands are affected by atmospheric effects due to scattering of the electromagnetic energy. This causes a degradation in the image quality. A black object tends to have some brightness, which is an error. Now, this error has to be removed. So, let us look at how this can be performed. Basically, there are three methods by which this can be done. First is physical modeling, second is histogram minimum, and third is regression. So, let us look at physical modeling. Well, these models permit reflectance to be adjusted close to their true value that might be observed under clear atmospheric conditions. These models provide a rigorous and accurate solution with flexibility to model a large variety of atmospheric conditions. However, there are many significant disadvantages. One of them is the quantum of data which is required in order to run these physical models, which means that many of the parameters have to be acquired and stored as the sensor acquires the image data. Further, this physical modeling requires complex models requiring the use of integrated computer programs. By and large, this activity or approach is adopted by those who are interested in studying the basis of the atmospheric conditions and their relation to the reflectance characteristic. However, a general user may not be interested in this particular method. The next method is histogram minimum method, in short known as HMM. As we have already seen, atmospheric effects are generally low or negligible in the infrared region and high in the visible region. When the histograms of the visible region are examined, the lowest value of the histogram amongst the visible bands is subtracted from the brightness value of all the pixels in the visible bands. It is one of the simplest and direct method for correcting atmospheric degradation. The advantage of this method is its simplicity, directness and universal applicability, as it uses the information present within the image itself. However, this method is an approximate one. The third method, which is regression method of correcting the atmospheric effects, tries to retain the concept of examining the brightness of each object within each scene and also accounts for the interrelationship between the bands. In this approach, a visible band is plotted against an infrared band and a best fit, that is least square straight line, is computed using standard regression methods. The offset A on the x axis, as shown in the figure, represents an estimate of the atmospheric correction to be applied for that particular band. The advantage of using regression method is that it can be used for local areas also. This particular slide shows the physical and the logical concept behind the regression method. Having done the radiometric corrections, now the geometric corrections have to be performed. It has been observed that all remote sensing imageries are inherently subjected to geometric distortions. Such distortions may be due to several factors, such as the perspective of the sensor optics, the motion of the scanning system, the motion of the platform altitude and velocity, the terrain relief, and the curvature and rotation of the earth. Geometric corrections are intended to compensate for those distortions which make the geometric representation of the imagery as close as possible to the real world. Many of these variations are systematic or predictable in nature and can be accounted by accurate modeling of the sensor and the platform motion and the geometric relationship of the platform with the earth. Other non-systematic or random errors cannot be modeled and corrected in this manner. Therefore, geometric restoration of the image to a known ground coordinate system must be performed. Now, let us look at the systematic and non-systematic errors in the remote sensing images, and these are discussed. First is systematic errors. In systematic errors, first let us look at scan skew. It is caused by the forward motion of the platform during the time required for each mirror sweep. The ground swath is not normal to the ground track, but it is slightly skewed, producing cross scan geometric distortion. The figure below conceptualizes the scan skew distortion. Next is mirror scan velocity. The mirror scanning rate is usually not constant across given scan and produces along scan geometric distortions. The figure below shows the actual path of the mirror with mirror angle against the calibrated motion path. It may be noted that this type of error probably is no more applicable in the current sensor technology which is being used, which is charge coupled devices. The earlier MSS sensors which carried a mirror type of scanning procedure, this type of error had to be accounted for. Next is panoramic distortion. The ground area that is being imaged is proportional to the tangent of the scan angle rather than the angle itself. Since the data are sampled at regular intervals, this produces a along scan distortion. This is conceptualized in the figure shown below, and the solid lines show the actual manner in which the data has been collected, whereas the dotted one shows the theoretical shape of the image that should have been there. Next is platform velocity. If the speed of the platform changes, the ground track coverage by successive mirror scan changes produces a along track scale distortion. Next is earth rotation. The earth rotates as the sensor scans the ground. This results in a shift of the ground swath being scanned, causing a along scan distortion. Perspective. For some applications, it is desirable to have images represent the projection of points on the earth upon a plane tangent to the earth with all projection lines normal to the plane. This introduces a along scan distortion. Now we come to the non-systematic distortions which are there. First is altitude. If the platform departs from its normal altitude, changes in scale occur. Next is attitude. One of the sensor systems axis is usually maintained normally to the earth surface and introduces geometric distortion. Having had a look at the systematic and non-systematic errors which could come into play due to various factors as discussed earlier, now let us look at the procedure by which these can be removed from the digital images or remote sensing data sets. This process is what we call it as geometric rectification. The basic purpose of carrying out geometric correction is to orient the original data collected so that it has the desired scale and the map projection, or simply we can say it is made planimetric. A map projection is a device for the representation of a curved surface on a flat sheet of paper. Different types of map projections have been developed. However, each projection tries to preserve only some property of the mapped area, and either it is uniform representation of area or shape or preservation of correct bearings. Only one such property can be correctly represented, though several projections attempt to compromise by minimizing distortions in two or more map characteristics. Further, informations extracted from remote sensing data may be used with other geographical maps or two adjacent images of an area, or multi-temporal images are to be used for assessing the changes that may have occurred. The satellite data has to be fitted to a coordinate system. This process of providing a coordinate system to an image is known as registration. Thus, the geometric corrections of remotely sensed images required when the image is to be used for one of the following circumstances: to transfer from an image to map a map projection, to locate points of interest both on the map and on the image, to bring adjacent images into registration, to overlay temporal sequences of images of the same area, and to overlay images and maps within a GIS. Another factor which causes error is the motion of the earth as the data is being collected by the sensor. In case of Landsat TM sensors, there are 16 sensors, that is, data for 16 scan lines are acquired at a given interval of time t. The next 16 scanned lines, that is scan line number 17 to 32, will be acquired at a time t plus 1. However, during the time period t and t plus 1, the earth has moved eastwards. So, the scan line 17 to 32 will start slightly westward than the scan line 1 to 16 and also end slightly before the eastward limit of the previous 16 scan lines. This causes a skew in the image coverage. The net effect of this can be seen in this particular figure. It may be noted that as the angular velocity of earth varies with latitude, so this skew becomes more prominent at higher altitudes. So, the geometric corrections process can be considered to include: 1. Determination of a relationship between the coordinate system of a map and image, or image and image in case of registration. Establishment of a set of points defining pixel centers in the corrected image, with that when considered as a rectangular grid, and define an image with the desired cartographic properties. And finally, estimation of pixel values to be associated with those points. The relationship between two coordinate systems, map and image, could be defined by two methods. First, the orbital geometry of the satellite platform, and the second is transformation using ground control points, or in short known as GCPs. So, now let us look at the orbital geometry model. Orbital geometry methods are based on knowledge of the characteristics of the orbit of the satellite platform. It is a simple method of correcting the coordinate system of the remotely sensed image using approximate orbital parameters. This method is suitable only for use for images that have been acquired from sensor having narrow angular field of view, such as Landsat TM and the spot HRV. However, it can be easily extended to deal with imageries with similar sensors, provided that the nominal orbital parameters of the satellite are known or can be estimated. Since the method is based on the nominal orbital parameters, the accuracy of the geometrically corrected image produced by this technique is not high. In the orbital geometry model, the corrections can be modeled in three sequential steps as enumerated below. First is aspect ratio, second is skew correction, and third is earth rotation correction. Aspect ratio. Each sensor, as per its instantaneous field of view, has a ground coverage which is known as its pixel size. As the sensor moves along a scan line, there is a small overlap. So, instead of a square pixel, it is now a rectangular pixel. In case of Landsat MSS, the actual size of the collected data is 79 meters by 56 meters against the design value of 79 meters by 79 meters. Thus, the shape of the pixel is to be restored back to its desired square shape. This correction is known as the aspect ratio correction and can be represented by the transformation matrix M1, where M1 can be defined to have 2 rows by 2 columns and the elements are as shown in the equation. Next, we come to skew correction. Low altitude satellites are generally placed in a north-south axis. However, to counter the forces due to flattening of the earth, precessing of the earth's axis and the forces due to the stars, it is not possible to place the satellite in a perfect north-south alignment. Landsat 1 to 3 has an orbital inclination of 99.09 degrees, whereas Landsat 4 and 5 have an inclination of 98.2 degrees. The satellite heading, that is across scan direction at the equator, is therefore 9.09 degrees and 8.2 degrees respectively, increasing with latitude. The skew angle theta at latitude L can be expressed as theta is equal to 90 minus cos inverse of the ratio of sin theta e over cos L, where E is the satellite heading at the equator and L is the center latitude of the image. Given the values of the coordinate system of the image can be rotated through degrees anti-clockwise, so that the scan lines of the corrected images are oriented in an east-west direction using the transformation matrix M2, where M2 can be represented as a matrix as seen here. Next, we come to the Earth's rotation correction. As the satellite moves southwards along its orbit, the Earth rotates beneath it in an easterly direction with a surface velocity proportional to the nadir point. To compute the displacement of the last line in the image relative to the first line, we have to determine the time taken by the satellite sensor to scan the image and the eastward velocity of the Earth. The time taken by the satellite sensor to scan the image can be found out if the distance travelled by the satellite and the satellite's velocity are known. Here, both distance and velocity are expressed in terms of angular measurements. So, if A is a point on the Earth's surface corresponding to the center of the first scan line in the image, and B is the corresponding point in the last scan line in the image, then the line AB represents an arc of a circle centered at the Earth's center. The angle at the Earth's center O is given by the angle AOB and can be calculated as the Earth's equatorial radius is 6,378 kilometers. So, further the orbital period of the satellite is known. Thus, the angular velocity of the satellite omega, which is equal to 2 pi divided by p multiplied by 60. The time t required to travel the angular distance AOB can be obtained by dividing omega by the angle AOB. Subsequently, we can determine the displacement of the last scan with respect to the first scan line. This is dependent on the central latitude L of the image. If the Earth's velocity at latitude L is given by v e L, it can be defined as being equal to r cos of L omega e, where r is the Earth's radius defined above and omega is the Earth's angular velocity. Since the earth rotates once in 23 hours 56 minutes and 4 seconds, that is 86,164 seconds, then its angular velocity is simply 2 pi divided by 86,164 radians per second, or this is equal to 0.7279 radians per second. Given the latitude L, now we can determine the skew angle theta. So, the actual displacement is omega 0 multiplied by t into cos theta. These computations are summarized by the term ASK, which can be simplified and written as 0.0719 multiplied by the ratio of cos L and cos theta, where the earth's angular velocity is omega e, is the satellite's angular velocity omega 0, and theta and L are defined as above. So, the transformation matrix 3 can now be expressed as it is shown at the bottom. The three transformation matrices M1, M2 and M3 are not applied separately. Instead, a composite transformation matrix M is obtained by multiplying the three separate transformation matrices. The corrected image coordinate system is related to the raw image coordinate system by x dash is equal to mx, where x dash is nothing but x1, x2, the vector defining the coordinates of the corrected pixel, and x is equal to x1 and x2 is the original coordinate. Now, we come to the next method, and that is the geometric rectification. Geometric rectification is the process by which the geometry of an image is made planimetric. It requires the use of GCPs whose image coordinates in terms of rows and pixel number are known along with the map or ground coordinates. It is an accurate process since each pixel is referenced not only by its image coordinates, but also by its ground coordinate system in a standard map projection, and hence it is known as image to map rectification. Geometric rectification has to be done when accurate linear or aerial measurements are needed. Many a times accurate geometric rectification is not needed, specifically when two or more images are used to find out the changes in an area or region. Here, instead of carrying geometric rectifications of all the images and then determining the changes, the images are registered with respect to each other. This is known as image registration or image to image registration. To remove systematic errors, it requires an in-depth knowledge of a large number of parameters related to the satellite ephemeris data, and these errors are corrected at the master data center. Generally, non-systematic errors are corrected by the user himself by selecting suitable number of GCPs. There are two geometric correction procedures, that is geometric rectification and geometric registration, which are generally applied. The difference between rectification and registration is that in rectification the image is referenced to a map having a standard map projection, while in registration two images are referenced to each other and do not have any map having a standard map projection. As most of the remote sensing applications yield a map, hence image to map rectification has been discussed in details. In this particular slide, it illustrates the procedure of rectification which actually has to be carried out. On the left hand side, we can see that there is one image which is tilted, which is the raw data, and the upright corrected image is shown on the right hand side, and we have to correct the tilted shape of the image onto the upright corrected shape as shown. In order to do so, we have to now define a system by which the tilted or oriented image can be made in a upright format. In order to rectify a remote sensing image to a map coordinate system, two basic operations have to be performed. First is spatial interpolation and second is intensity interpolation. In spatial interpolation, a large number of GCPs are identified on the image and on the ground. A polynomial is fitted to the control points using least square criteria to model the geometric error directly into the image without explicitly defining or identifying their source. Generally, a 6-parameter affine transformation is sufficient to rectify a remote sensing image, as it can model for 6 kinds of distortions, that is, translation in x and y, scale changes in x and y, and direction and skew and rotation. Thus, this can be expressed mathematically by the following equations: x dash is equal to a0 plus a1 x plus a2 y, and y dash is equal to b0 plus b1 x plus b2 y, where x and y are the ground coordinates values and the x dash and y dash are the image coordinate values. It may be noted that minimum of 3 GCPs can yield a solution. However, more than 3 GCPs are used to compute the coefficients a0, a1, a2, b0, b1 and b2. This method involves the computation of root mean square error for each GCPs, where the root RMS error can be expressed as under root of x dash minus x0 whole square plus y dash minus y0 whole square, where x0, y0 and x dash and y dash are the original and the computed image coordinates of the GCP respectively. By computing the RMS of all the GCPs, it is possible to identify the GCP which exhibits the greatest error and also the sum total of the RMS error of all the GCPs. Generally, the analyst specifies a threshold value for the total error. If the total error exceeds the threshold value, the GCP having the largest individual RMS error is deleted and a new set of coefficients of a0, a1, a2, b0, b1 and b2 are computed. This process is an iterative in nature and continues till total RMS error of all the GCPs is within a user specified threshold, or that the number of the GCPs fall below an unacceptable limit, usually 3. Once the acceptable RMS error is achieved, the intensity interpolation of geometrically rectified images start. So, now let us look at the intensity interpolation. After the spatial interpolation is carried out, the next step is to extract or identify the brightness value of the new image from the old image. This process is known as resampling. The resampling process calculates the new pixel values from the original digital pixel values in the uncorrected image. There are 3 common methods for resampling. nearest neighborhood, bilinear interpolation and cubic convolution. So, let us look at the first method, that is the nearest neighborhood. Nearest neighborhood resampling uses the digital value from the pixel in the original image which is nearest to the new pixel location in the corrected image. This is one of the simplest methods and does not alter the original values, but may result in some pixel values being duplicated while others are lost. This method also tends to result in a disjointed or blocky image appearance. This particular figure shows the concept of nearest neighborhood intensity interpolation, wherein we on the left hand side we have the original input image and on the right hand side we have the rectified output image. We first find out what is the relationship between these two, and on the basis of that we find out where is the center of the pixel in the rectified image lies on the original input data. In this particular example, we can see that the center of the rectified output image is not coincident with either of any of the points which specify the center of the pixel. It lies somewhere in between. Now, it has to identify to which pixel it is closest to. In order to do so, one will find out what is the equivalent distance between the pixel center to the superimposed position of the rectified output image pixel. Whichever distance is the minimum to that particular pixel brightness value will be adopted for the new pixel in the rectified image. Then we come to the bilinear interpolation. Bilinear interpolation resampling takes a weighted average of all the 4 pixels in the original image nearest to the pixel location. That is, as seen in the previous slide, wherein a graphical depiction of the location of the rectified pixel and the 4 nearest pixels lying in the close vicinity have been shown. In bilinear interpolation, what is done is that all the 4 points, their weightages or their values are taken, and they are multiplied by the inverse of the distance, or one can say the inverse weight is provided to the brightness value or the 4 pixels which surround this particular pixel. So, this can be expressed as BV nu, which is equal to summation of all the 4 pixel brightness values divided by the inverse of the square of the distances of these points. The average process altered the original pixel values and creates entirely a new digital value in the output data. The third method, which is cubic convolution, it even goes one step further to calculate the distance weighted average of a block of 16 pixels from the original image which surround the new output pixel location. As in bilinear interpolation, this method also results in a completely new pixel value. However, both the methods produce images which are sharper in appearance and avoid the blocky appearances of the nearest neighborhood method. Having discussed these, now let us look at a comparative evaluation of these 3 resampling technique methods. This particular table, as a matter of fact, provides the basis of the methods which are there, that is, in nearest neighborhood, the technique basis is that it transfers the brightness value of the nearest pixel The relative complexity in computing can be set to 1 in this particular case. The advantage of using nearest neighborhood resampling technique is that it is simple to compute array values which are unaltered. Disadvantage that this particular method has, that the image appears to be disjointed or blocky in nature. The next method, that is bilinear, it is a proximity based weighted average method from the nearest pixel. The complexity in terms of computing relative to nearest neighborhood is 10 times. Advantage is that the image is smooth and geometrically accurate. However, in this particular process, the brightness values or the gray values of the original image may get altered. Cubic convolution, again a proximity weighted average method of 16 nearest pixels, has a relative complexity in terms of computing with respect to nearest neighborhood of 20. It produces a very smooth image. However, it is complex to compute and the gray values gets altered. Having done this particular process of rectification and restoration, now the original data has been actually made to be tied to the earth such that it bears a well defined relationship amongst the image and the ground points. This results in one unique aspect, and that is all linear measurements or area measurements computed with the help of such a rectified data do not have any errors. In my next session, I would be then proceeding on to the next part of the image analysis process, which is image enhancement. Thank you.
Thank you.